Hello and welcome to my video on further engineering mathematics data analysis. This time we're focusing more on correlation. Now, correlation is a term for the measure of strength of a linear relationship between two quantitative or numerical quantities or variables. So let's look in at correlation a bit. Now, the general types of correlation are we can have a positive linear correlation as shown on the graph on the left, as it increases in value as our independent value x increases. We can have a negative linear correlation where our y value decreases as our independent value x increases, as shown on the right. We can have no correlation at all between the two values, so all the data points are scattered randomly around the graph. And within the original two sets of correlation, we can have strong correlation, shown here on the left, where it's very evident and quite clear that there's a straight line there. Or we can have a weak correlation, which we can see on the right, where you can see it's increasing, but it's not entirely obvious where that line's going to be. This is the graph that we'll most likely find when we draw a graph from our own testing with our own results. So the degree of correlation determines how well data correlates with the independent value, and it can be given by a formula. So R is our degree of correlation, and it's equal to the sum of AB divided by the square root of the sum of A squared times the sum of B squared. Now, these new variables A and B will generate from our table and from the data that we put into it. They don't have any values or anything set to them right now. They could be any letter we want. So if we're looking at a little x and a little y, you could also set these variables to be a capital X and a capital Y. It's completely arbitrary what values we set these to. So we're going to go through an example. We've generated some data, and I have an independent value here on the left and a dependent value y. I've then graphed it here, and you can see that there is some degree of positive linear correlation between my independent and my dependent values. We could apply a line of regression to this, and it will give us an equation. And this is very useful. It doesn't look like my data points have any particular outliers apart from maybe when my x is equal to 0. So this is, as you're going through it, these are things that you need to make a note of and consider as you go through. So the first thing we're going to do with our data table is we're going to add a new row at the bottom where we're going to calculate the sum of all the values that are above it. And I'm going to make that dark gray. If it's in a dark gray box, it's the sum of that column. And then I'm going to calculate the average value of x. So I'm going to take the sum of x and divide it by the number of terms. So in this case, it all adds up to 45. There's 10 values, so I'm going to divide it by 10, which is 4.5. And then what I'm going to do is I'm going to make a third column. And in this third column, I'm going to subtract the mean from the original independent value of that row. So in the first row, I'm going to have 0 minus 4.5. In the second row, I'm going to have 1 minus 4.5. And that's going to continue all the way down. And I'm going to label that column A. And now I'm going to do exactly the same thing for my y values. I'm going to sum up all my y values, divide it by the number of terms, and I'm going to get an average for my dependent value y, 27.6. I'm going to make my fourth column, which I'm going to call column B, and that's going to be y minus y bar. And that looks something like this. Now, expanding on the data table a bit more, and to help with that equation we just saw, I'm going to add a fifth column, which is going to be A times B for each row, and at the bottom, I'm going to take the sum of those values. And then I'm going to add a sixth and seventh column, which is simply going to be A squared and B squared, respectively, and I'm going to sum both of those at the bottom. And there we have it. That's my complete data table. I'm now going to take these values, particularly the ones in the gray row at the bottom, and I'm going to put them into the equation we saw earlier. And here it is. So again, R is equal to the sum of A times B divided by the square root of the sum of A squared times the sum of B squared. We put the values from a table in, we get 386 divided by the square root of 82.5 times 19.04. Now, we put the values in, we're going to go through BIDMAS, so that's brackets, indices, division, which coincidentally are the three things that we have. So working out the inside of the bracket first, 82.5 times 1904.4 is 157,113. Taking the indices, which is the square root of that, we get 396.37. And then finally, we divide 386 by 396.37 to get 0.97. Now that 0.97 is our correlation ratio. And we're going to expand on what that means now. So the value we calculate for R needs to be compared to this table for an explanation. Now R can have a range of values between 1 and -1. If it's 1, we have a perfect direct correlation. If we have a -1, we have a perfect negative correlation. If it's bang on 0 in the middle, no correlation exists at all. But we also have a sliding scale. If it's plus 0.9, we have a very good correlation. If it's between plus 0.7 and 0.8, we have a fairly good direct correlation. And if it's between 0 and 0.7, we have no appreciable correlation. Conversely, on the negative side, if R is equal to minus 0.9, we have a very good negative correlation. If R is equal to minus 0.7 to minus 0.8, we have fairly good negative correlation. And if R is greater than minus 0.7, but less than 0, we have no appreciable negative correlation either. We come back to our value for R, which is 0.97, compare it to the table, and that shows we have a very good correlation between the two. Thanks for watching. I hope this video has helped. I'll speak to you in the next one.